So we've seen here that if X is doubly ergodic, then X is ME is metrically ergodic. I think Miel will explain that this is later. This is not if and only if. Not if and only if. But there is a converse in the fact theorem. Why not? If G act on X is PNP, probability measure preserving. So not just preserving a measure class, but preserving an actual measure and a finite one. Then G act on X squared ergodic if and only if G act on X metrically ergodic. In fact, for PNP action, the following are equivalent. And now I will give just 3 equivalent definitions out of a list that can be made arbitrarily long. In my notes I have 6 equivalent definitions of property, this property, metric ergodicity property in the PNP world that is called weakly mixing. So either of these equivalent definition, and most of the time this one.
Weakly mixing means what exactly?
This. Oh, I'll write down okay, I write 1, 2, 3 here, and then I will write the definition. 1. Maybe 1. This is the property that you may think of as stably ergodic. For every other ergodic action, the action on X times Y is ergodic. So this is stably ergodic. 2. Doubly ergodic. These are all property of G acting on X. G acting on X is given, and 1, 2, 3, 1, 2 so far, are properties of the action on X. And 3, G act on X is ME. Any question about this formulation?
Without PNP, how much of this is left?
So we've seen that this implies that actually 1 implies 2 implies 3. Is left.
Of course. Yes. That's obvious. And the reverse are false.
And ME implies, 3 implies 1 is what is needed for. So, just a minute.
Is this the same as L2 does not contain finite?
Yes, I said this is the same, if you are familiar with this, as L2x paired to the constant does not contain any finite dimensional subrepresentation. I will not write this one down. G acting on x, assuming PMP is called weakly mixing. This is just a classical name. And of course there is a stronger notion of mixing, and the stronger notion of mixing is exactly that one that we proved about, the Haumu theorem, vanishing of matrix coefficients. I will not write it down, maybe it will appear in the exercise sheet. Is called weakly mixing if the equivalent property above are satisfied. Another remark that we have mainly seen. 1 implies 2, I think we all believe that. Implied 3, 2, without assuming PMP. We'll show for PMP same time. Okay, so this is what we do. Any question? So, assume G act on X ME, G act on Y ergodic. And I want to show that L infinity x times y is trivial. So take a function here. I want to show this function is constant. So trick is very easy. Using Fubini, I can think about this function as a map from x to L to y. Right? I mean, for almost every point in x, the function f is defined for almost every point in y. This is Fubini. And I leave it to you to check. This, the G equivariance of, the G invariance of the map F is the G equivariance of this new map. But this is a metric space. But my ME of X, this is constant. Is a constant in L to Y, and this constant is G fixed. But by ergodicity of Y, these are the constants. So for almost every X, I got the same thing that gives me for almost every Y, same constant. So f is constant. And we get that we get ergodicity. Okay. So metric ergodicity, if you are familiar with, this is helpful to think of as a generalization, a nice generalization of the property known as a weak mixing, which is very important in ergodic theory. Okay. Now, back to SLN. What do we have there? Here. Any questions so far? For SLNR, actually, every ergodic action is automatically metrically ergodic. So, what I just said is completely is bullshit. SL2, SLNR is isometric actions. For example, G acts on G mod K. SL2R acts on the hyperbolic plane with a standard measure and a standard metric. It cannot be metrically ergodic. But what I meant to say is every probability measure preserving action is automatically ME. Every ergodic cell. Okay, so one can deduce this from the fact that actually every action is mixing. This is how move. So you may know this. But let me give an independent proof, or related proof, but very neat in our context. So we need to show and I hope by choice of letters the notation will be clear. For every G map from X to an isometric G action is constant. And in UG. Of course, just by the fact that if X is mapped to the invariant points, the image is constant by ergodicity. If there was no action of X, if there was no action on U, and you try to map X into U, this will be an invariant function into a nice space, and the image must be a point, a delta measure at a point, the image measure. So we might as well assume that, let's remove this subset. Assume now, by contradiction, that there are no fixed points. Either I'm hitting fixed point, or I'm hitting the set of points which are not fixed. Assume by contradiction that I didn't hit that set. X hits the complement. So I'm assuming that U has no fixed points. Or maybe one more word about it. X is ergodic. U has two pieces, the invariant points and the rest. By ergodicity, X will hit one of these. Either it hits the invariant points, and then it must hit one point. And the map from X to U is fixed, is constant. Or X hits the rest. So here I'm considering this case. I'm considering the map from X to the complement of the fixed point. So I might as well assume that there are no fixed point in U. And I should get the contradiction to the existence of such a number. We know now that the action of G on U is proper. Consider the image measure on U. So I think of the image which is pushed to U. And take K in U compact with more than half the measure. Then, what will be the measure of GK? What to be at least? Be at least 1/2 as well, right? And the intersection with K will have some positive measure as well. This is not 0. And this is happening for every G. And this contradicting. Properties.
I have a little doubt. You remove the fixed points,
Yes.
and you claim that the rest is proper as well.
No. I removed the fixed point, and then I was assuming that there are no fixed point. So on the rest, G act. G act on this metric space with no fixed point. G is SLN.
Oh, okay.
And this is a theory that we proved yesterday. Every action with no fixed point.
Sure.
And this is a theory that we worked for. It's not a triviality. Okay, so let's gather some corollaries. For example, the action of G on G mod gamma is ergodic. Do you agree with that? You must agree. What about G mod gamma square? Well, it follows from that, right? If it is ergodic, it is metrically ergodic, and if it is metrically ergodic, then the action, because G mod gamma, well, I didn't tell you, but you understand, gamma is lattice in G. So this, for G being SLN R, gamma in G a lattice. So, should be so the action of G on G mod gamma square, or actually G mod gamma to the n, I claim, is ergodic. The action of G on G mod gamma square, because it is a lattice, after normalization, this is a P and P action, and because we proved that the action of G on G mod gamma is NE, the action of G on G mod gamma is obviously ergodic, hence by that term it's NE, hence it is doubly ergodic, and the action of G on G mod gamma is ergodic. that's doubly ergodic, or actually stably ergodic. Now take y to the G mod gamma, and go on, in that. Maybe another, I forgot to do this, it's observations. That I should have done before. G, which is again SLN now, act on X, ergodic, and by the way, metrically ergodic. H in G, non-compact. Then also the action of H on X is ergodic. And actually metrically ergodic. Let me explain this. First of all, why is metrically ergodic? If I would prove that it is ergodic, metergodicity will come easily because just consider the action of G on X squared. It is ergodic as well. And restrict that one to H. It is ergodic by what we are about to prove. And if H acts on X squared ergodically, then it acts metrically ergodic on X by PMP. So I'm forgetting. So why is that? Consider L2XH. Can we have fixed point here? H fixed point. This is a trick that I made before. This is the same. If you have H fixed point, this is the same as a map from G mod H to L2X. Right? I mean, just take the orbit of that H fixed point. Whenever, but okay. Now I just have to say metric ergodicity. And this is the same as, or equivalent to L2X G. This is metric ergodicity of G mod H. Right? I mean, you cannot map G mod H into this metric space unless you hit a G fixed point. And these are the constants. Okay, so this corollary gives me same notation. H acts on G mod gamma to the n is ergodic. With these notation, of course. G is SLN, gamma is lattice, A is non-compact in G. So we get these for free. It's ergodic and metrically ergodic. In particular, H acts on G mod gamma metrically ergodic. And this can be reversed. Third, again, G is SNR, gamma a lattice, H in G not compact. Then also the gamma action on G mod H is metrically ergodic. Actually, this guy is followed from a general plane. So G act on G modate metrically ergodic. So if G act on X metrically ergodic, not necessarily probability measure preserving here. Gamma in G lattice, then also the action of gamma on X is metrically ergodic. Let me give you that one. So, of course, the general claim for X equal G mod H gives that here. For this general claim, G need not be SLN or anything. So, proof of that. I want to show that this guy is metrically ergodic. So with obvious notation, I want to show that there are no maps from X to U, gamma maps. This is gamma act by isometries here. And this is an actual G space. And I know that G act ME on that one. But unfortunately, there is no G structure here, and this map is only gamma. But if you are familiar with induction in representation theory or its analogs in ergodic theory, this is what I'm supposed to do. This is the obvious things I'm about to apply, and let me do it very explicitly here. So we consider a new map. I will consider a map from G times G mod H to U, just somehow to force some G structural things. So I should take G, comma G prime H to some element. Let me. Yeah, okay. So, in my notes I was less general. Nothing bad will happen by that. So I need to send Gx to U, and no much I can do. There is no G action on U. I will act before. I will act by G inverse here on X and apply phi. Can you see from that corner? Okay, so this is the new map I'm using, and now again, if you wish Fubini, I think of G as a measure space. This is a map between two spaces. G is a measure space with the Haar measure, X with some measure which is implicit in our discussion, and I have this product space and a map to some nice Borel space. Again, I can use Fubini and think of this map as a map from X to the space of maps from G to U. And L means space of maps. Actually, I will elaborate on these kind of notations probably tomorrow. Again, on the very definition of the backspace, etc., which I'm postponing and probably I'm making a mistake here. But so this is the space LGU is a space of all maps defined up to measure 0 from that Lebesgue space G into U. But we have started with an equivalent gamma equivalent function phi. If we apply gamma to G on the right, or this like time gamma inverse on the right, this is the right action. It will come as gamma on the left here by inverting G, and phi is equivariant, so it will come here. Right? So what I'm trying to say is this is the space of this is actually the space of gamma evariants. Moreover, if I apply G to that X on the left, it is the same as applying G to, I can interchange, since I'm taking G inverse X here, I can apply, I don't know, G prime on the left of that G and on the left of just that X without doing a thing. And what I'm trying to say here is that this is a G map. What I'm getting here. But just to be precise, this is on that space, ignore this gamma here, on the space of maps from G mod U, from G to U, I have two G actions coming from the actions of G on the left and on the right of G. And this map, the maps here that you will get will be equivariant for the right gamma action, and there will be a left G action, and this map will be invariant, equivalent for that left G action. And I leave it for you to check if this is a formula which basically with my fingers I try to explain, but it is better if you write down if you can see it. Okay, blah 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 blah. But now, this space, the space of gamma equivariant map from G to U, what I want to claim is as a natural structure of a metric space. Maybe I'll. Assuming now, what I can, that the metric on U is bounded, which as we remarked before, we can assume in the definition of metric bodicity, there is a G invariant metric, basically an L1 metric, on the space of gamma equivariant function from G to U. And this is basically integrating the U value over a fundamental domain for gamma. For two guys, alpha and beta, functions, maybe I'll write it, elements here, but let me write it explicitly. Functions from G to U, gamma equivariant, I will define the distance, maybe I'll use another letter, the distance between alpha and beta to be integral of alpha. Now I'm using the distance in U, alpha x, beta x, dx, and this is integration over G, but on some finite measure subset.
Over G mod gamma.
Over G mod gamma, if you wish. Yes.
Gamma invariant.
Yes, since they are gamma invariant, no, they are not gamma invariant, they are gamma equivariant.
No, but this D of alpha x beta x.
Yes, D of those things is invariant. So just the alpha x will vary if I will. Okay, I will write G mod gamma in. Alpha x will vary if I apply little gamma to x. Also, beta x will vary. But D of these two things will not, since the maps are gamma equivariant, and the metric D is gamma invariant. So actually, yes, I was about to write that F is a fundamental domain, but this makes sense to write it over G mod gamma. This is well different. I suggested here, and this is bounded by 1, and this is the probability space. So this guy makes sense. So this big D is a G. This is a G metric space. Maybe I should write 1 here to denote that this is big D is the metric campus area. Okay, and since I was mapping X G equivariantly into this G metric space, and since X is assumed to be GME, this map here is constant. So it means that this map here does not depend on the X coordinate. Right? This is just the same thing. But what is this map? It does not depend on the X coordinate. Well, it means that the map phi was actually constant. ME for G implies that phi is constant. Okay. So what we have done so far. Last lecture we've seen that whenever G, our favorite groups, SLNs, act on metric spaces, well, the action is trivial in the following sense. Either you have fixed points, or the action is proper. In particular, if you consider actions of G on G mod H, coset spaces for H non-compact,